Hello students, in this video we'll see an example of computing an inverse Laplace transform using the Bromwich inversion integral in a case when doing it with the differential equations method of convolution would be much more cumbersome. Let's find the inverse Laplace transform of s over s squared plus a squared, where a is a positive number, over squared, using Bromwich. Great. So of course, there's going to be two singularities over here, and the cool thing is that you can see that one singularity is the conjugate of the other singularity. Let's examine that idea first. So let's recall that if z equals, let's say if z equals alpha plus I beta is a pole of f tilde of z, then the residue of f tilde of z times e to the zt at z equals alpha plus I beta is going to be what? Is going to be the sum of this polynomial. So if there's a pole, let's say there's a pole of f, is going to be equal to what? Is going to be equal to e to the I alpha plus I beta t. And then it's going to be b1 plus b2 t over 1 factorial, all the way down to bk t to the k minus 1 over k minus 1 factorial, like that, where b1 over this z minus alpha plus I beta plus bk over z minus alpha plus I beta to the power k is the principal singular part of this function f tilde of z near the pole alpha plus I beta, where is the principal singular part, right? Okay, excellent, great. Now, what do I know about f tilde? I know that f tilde is on the real axis is real. So by the Schwarz Reflection Principle, I know that by Schwarz reflection, principle, we know. And this shows the strength of complex analysis. I'm using sort of a big theorem in complex analysis to basically handle inversions of the Laplace transform. Okay? By the Schwarz reflection principle, we know that f tilde of z bar has to be equal to f tilde of z bar, which forces alpha minus I beta to be a pole. This forces alpha minus I beta is also a pole. Okay? And so what's going to happen over here? Well, when I find the residue at the pole point, what will that be? The residue at the pole point, at the conjugate point, f tilde of z e to the zt at z equals alpha minus I beta is going to be equal to what? Is going to be e to the alpha minus I beta t. And then what? And then I have to do all the what? I have to do all the conjugates over here, right? So b1 conjugate plus b2 conjugate t over 1 factorial, all the way down to bk conjugate t to the k minus 1 over k minus 1. So that's a k minus 1 factorial, like that. And now I can add these two things together, right? Because now they come in pairs, right? So if I pair these off, I can say that the sum of the two residues, so the residue of f of z e to the zt at z equals, let's sum over plus minus over here. I'm going to sum over plus minus. Z equals alpha plus minus I beta is going to be what? Is going to be 2 e to the alpha t, like that. And then it's the real part, right? Because the real part is this plus its conjugate, right? So the real part of b1 of e to the I beta t times the expression b1 plus b2 t plus plus bk t to the k minus 1 over k minus 1 factorial, okay? Beautiful. This formula is extremely useful because it gives me a quick way to compute residues very fast. So now, with that little bit of a lemma over here, so let's call this whole expression over here a lemma to do this calculation, what can we say? Well, now let's return to our problem. Our problem now says, well, what do we have? I'm only gonna look at the ones, I'm gonna factor our problem as s over s minus ia squared, and then s plus ia squared, right? Good. And let's just focus on the expression IA, right? So the singular, the residue at A, right? So now, what can I say about the residues? So the residue of this thing how we're going to compute that? Well, it's just going to be this function over here. I have to Taylor expand this function over here. So let's call that function over there, let's call it g of s. So how we're going to do this is going to be g of s is going to be g of IA plus g prime of IA. That's my B1. That's my what? We'll find out what B1 and B2 are going to be over here in a second. Okay? Good. So, good. So what will the g, this is going to be the B what? The g of IA is going to be the B1, and then the g, what will that be? That's going to be the B2 actually, I'm sorry. That's going to be the B2, not the B1. So it's going to be g of IA plus g prime of IA, and then z minus IA, or in this case, s minus IA, right? S minus IA. Those are the only two terms I need, etc. So when I hit this with, if I hit g with s minus a, what do we see? We see that this expression over here, s over s minus IA squared times s plus IA squared is going to be what? Let's write out the principal part of this thing over here. So the principal part is going to be what? The principal part, so the g of IA is going to be the b what? Is going to be the B2 in this thing over here. So this is going to be a B2, so it's going to be g of IA over s minus IA squared plus g prime of IA over s minus IA to the single power, and the rest of the terms are irrelevant, right? I only need those two terms. Okay, so what's the g of IA going to give me? The g of IA is going to be that's going to correspond to what? G of IA is going to correspond to the B2 term, right? That's going to be my B2. That's going to be my B1 term over there. Good. So what's my B? What's g of IA? So g of IA is going to be equal to what? It's going to be equal to IA over, then IA, 2IA squared, that's going to be a negative 4a squared, so that's going to be a negative I over 4 times a, like that. Good. What's g prime going to be? G prime is going to be what? G prime is going to be the bottom times the derivative of the top, s plus IA squared, minus the top times the derivative of the bottom, 2, and then s plus IA times s. And we plug in IA to that, what's going to happen over here? We're going to have a total of what? S plus IA to what power? S plus IA. So it's the bottom times the derivative of the top, good, minus the top times the derivative of the bottom, or the bottom squared. That's going to be a 4, right? And this tells us that g prime of IA, hence if I plug in IA to this, I'm going to get a 2IA squared, that's negative 4 squared. Plug in IA to this, I'm going to get what? A negative a squared again with a 4, right? So that tells me when I plug in IA to this, we're going to get a total factor of what? We're going to get nothing. So this says that g prime of IA is equal to 0. Great. Okay. Let's just double check that. So it's going to be 2IA squared, right? So that's going to be a negative 4a squared, right? So if I plug in IA over here, that's going to be a 2IA, negative 4, and then negative I, that turns into a positive, so that's going to cancel out. Good. Okay? And so now we're in the position to find the Laplace transform, because now what do I have over here? So now our Laplace transform is going to be, the inverse Laplace transform is going to be Let's see, we're going to have a 2. We're going to have an e to the what? My alpha is 0 over here, 0t. Then I have the real part of what? The real part of e to the beta is equal to I, so it's going to be e to the I a t. That's what my beta is. It's my a over here. And then my b1 is equal to 0. That's gone. My b2 is equal to a negative what? Negative ia. The a is in the denominator over here, like that. So let's put the a in the denominator. Good. Okay. And then I have a negative I over 4, and then an a like that. Good. All right. And so, of course, what is the real part of this thing over here? So the real part of this thing, so this is going to be, let's recall what this is going to be. So e to the iat, this is going to be, so I'm going to pull that 4 and that a out. So that's going to be a 1 over 2a, 1 over 2a, like that. And then what will we have over here? And of course, there's a t as well, right? I mean, it might be 2 times t. That t is going to come out. That's a real parameter. And then you're going to have a what? Then you're going to have a sine of t. Now you have an I times negative I, so I times negative I is going to be a positive, so it's going to be a positive sine of a t. And there is the inverse Laplace transform of this expression. With a little bit of legwork and a little bit of Taylor expansions, we're able to quickly deduce what these inverse Laplace transforms are. And actually, most of the work, the bulk of the work, came in this part over here. The rest of it was fairly straightforward, just doing a Laurent expansion, right? The Laurent expansion is the easy part. Coming up with the reflection principle is the hard part. Nonetheless, this methodology, as we'll see in further videos, will extend to the case when there's an infinite number of singularities. We'll just let that circle that encapsulates all the singularities go to infinity. In this case, we'll be able to find a wide collection of inverse Laplace transform where there's an infinite number of singularities of the Laplace transform that's given. Thank you very much.